We know so many of you are trying to figure out how these complex AI systems go from being, interesting research projects to something you can actually rely on, something audit ready for real enterprise operations. Well, today we have the perfect case study. Welcome to the deep dive. We are cracking open the technical blueprint for a system called True Clarity AI Predictive Ordering 2.0, or AIPO. And this isn't about an AI that guesses the future. It's about a very specific architectural innovation, a new fine-tuning method that makes inventory management trustworthy, especially when operational rules are, well, non-negotiable.
It's an essential conflict they're trying to solve here. You have these high-stakes systems, supply chain, finance, compliance, and they're all starting to use large language models as reasoning engines. But here's the problem. LLMs are probabilistic. They're designed to make these incredibly informed contextual guesses. And when you inject that uncertainty into a domain that needs exact repeatable results, we need exactly 48 units of this, you create a huge amount of risk. The model's precision just falls apart. We really need to look at how AIPO 2.0 handles that tension.
Okay, let's start with the groundwork then. Where does a system like this actually fit into a company's existing tech stack?
It's really designed for what you'd call low friction. True Clarity built it to integrate directly with Microsoft Dynamics 365 Business Central, and it doesn't matter if it's on-prem or in the cloud.
Okay.
But the core ideas, the architecture, it's pretty universal. It could easily be adapted for other big ERP systems like SAP.
And the installation itself is built around being non-disruptive, correct?
Exactly. The solution is entirely non-intrusive. It's read-only. It never writes anything back into the core ERP.
So it's not messing with daily operations at all?
Not at all. The sources say a standard installation is incredibly fast. We're talking maybe half a day to deploy. And that speed is only possible because they found a way to sidestep a massive data integrity problem.
And I'm guessing that problem is the quality of the inventory data itself, right?
Precisely. For anyone listening who worries about data purity, this is so important. AIPO 2.0 deliberately ignores the live inventory balances, the numbers that are constantly changing and are often kind of messy.
So where does it get its signals from?
It derives everything from historical posted ledger activity, your sales history, your purchase history, the settled audited facts.
Why is that approach so revolutionary in practice?
Because it means you don't need a perfectly maintained, fully implemented inventory module. Think about distributors or wholesalers. Their on-hand quantities might be incomplete. Maybe some stock is managed outside the system. If your model needs perfect perpetual inventory, it's going to fail right away. By anchoring to historical turnover, the flow of goods, the system becomes so much more reliable.
That makes the barrier to entry way lower for businesses whose ERP setup is, let's say, functional but maybe not flawless. So once AIPO generates these suggestions, how do people actually use them?
The output is just structured CSVs, so you can use Excel in a pinch, but the documentation really recommends using Power BI.
For governance, I assume.
Absolutely for governance. Power BI turns all those numbers into visual audit tools. It makes the whole process transparent. You can see the logic, compare the AI's idea to a human override, and really build that stakeholder confidence in a way a giant spreadsheet never could.
This brings us right to the core problem AIPO 2.0 is designed to solve. Why does the traditional way of applying AI here just break? Let's start with the basics. What's the real difference between training an LLM and fine-tuning it?
Right. So training a foundation model, that's a massive undertaking. We're talking hundreds of millions of dollars, specialized hardware running for months on end. The result is a model with general knowledge about, well, everything.
And fine-tuning.
Fine-tuning is much lighter. It's about adapting that generally smart model to a very specific task using a small specialized data set.
Okay, so what do most companies do when they try to fine-tune an LLM for inventory?
They fall right into a trap. It's called outcome-centric fine-tuning. They just feed the model thousands of examples like, for item A, we sold X units, so the correct order was Y units. They're teaching it historical answers.
Instead of teaching it the rules.
Exactly. And the consequence of teaching a language model specific answers is something the sources call item identity leakage. The model just starts memorizing the behavior of individual SKUs. It doesn't learn the principles of ordering. It just learns that this specific item behaves in this specific way.
So when a new item shows up or a supplier suddenly changes their lead time, the model just freezes up or it starts guessing.
It's worse than guessing. It produces these overconfident but profoundly incorrect extrapolations. It's fragile, you know? It only understands the narrow slice of data it was trained on. It's like studying with flashcards for a test instead of actually understanding the subject. The minute you see a new question, the flashcard model just fails.
This is a perfect segue then. The conclusion from the systems architect was that you just can't rely on the model for correctness. You have to enforce it from the outside.
That's the core thesis. Reliable deployment means you have to assume the model will make an error by default. You have to build an architecture around it that acts as a strong deterministic safety net.
And this is where we get to the big innovation. Let's unpack this unique methodology, guardrail-centric fine-tuning. What is the central shift in thinking here?
The shift is pretty radical. They just stopped trying to teach the model the answer. Instead of aligning it to item-level outcomes, they aligned it only to these generalized, domain-agnostic behavioral constraints. They call them guardrails. They came up with about 50 of these guardrails and applied them to a quantized version of the quencoder.oneform-B model. The key is that these rules apply equally to any item, any vendor, any product category. They're universal.
Can you give us a few tangible examples of what these guardrails actually do?
Yeah, of course. They basically encode operational reality into digital rules. For instance, one is coverage-based ordering. The model has to make sure any order covers a 21-day cycle plus the supplier's lead time, period.
Simple rule.
Or unit of measure integrity. No matter what the math says, the model can never suggest ordering a partial case or an open package.
And then there's my favorite bit of jargon, tie-high snapping.
Yes, tie-high snapping. All that means is the final suggested order has to conform to the physical packaging. So, you're always ordering a full layer on a pallet, or maybe a full pallet. It just prevents logistical headaches down the line.
So the fine-tuning teaches the model how to think about inventory, not what to order. This is so critical because it means the model keeps its general smarts. It can handle a brand new product line or a weird seasonal spike without just breaking.
That preservation of capability is why their choice of model is so interesting. They chose the 14 billion parameter variant, not the larger 32 billion one, which you'd think would be smarter.
Wait, hold on. Why would the smaller, supposedly less powerful model do better with numerical logic? What was the bigger one doing wrong when it over-reasoned?
It's fascinating. The 14B model just gave them much more stable and consistent outputs, especially with multi-step math. The 32B model, with its greater capacity for inference, it sort of tried to get too clever. It would introduce these unintended connections based on subtle patterns it thought it saw in the data, which led to this subtle, unpredictable drift in the results. And on top of that, when they quantized the models, compressed them down to 4-bit or 8-bit for efficient local deployment, the smaller 14B model just held up better. It really proves that for these kinds of constrained enterprise tasks, stability and consistency beat raw power.
That's a huge lesson. Bigger isn't always better when discipline is the goal. So how is this disciplined thinking actually enforced by the system's architecture? You mentioned a mandatory separation.
Yes, the system is a hybrid. It explicitly separates probabilistic reasoning from deterministic execution. This separation is the absolute key to making the whole thing auditable and explainable.
Okay, let's break down those roles. Who does the thinking and who has the final say?
So the LLM's role is interpretation, reasoning, and generating the rationale. It's the advisory engine.
But its output isn't taken as fact.
Never. The absolute authority is the Python layer. That's where all the deterministic math lives. The coverage calculations, the unit of measure conversions, the layer snapping. If the model suggests something that violates a rule, the Python layer just overrides it instantly.
And there's another layer before that, right? This pre-processing step.
Right. Even before the LLM sees anything, there's a crucial step called deterministic pre-processing. A profiler runs over the historical data and classifies each item's behavior.
What kind of classification are we talking about here?
It's using standard heuristics, things like the average demand interval, ADI, and the coefficient of variation squared, CV. Think of it this way. ADI tells you how often an item sells. Is it daily or once a quarter? And CV tells you how wild the demand is. Is it smooth and predictable or totally lumpy and chaotic? So this step basically frames the problem for the model. The LLM gets told, this is a smooth demand item, not just a raw stream of noisy numbers. It stops the model from wasting its energy on complex pattern recognition when it's not allowed to have decision authority anyway.
In systems like this, developers often use something called chain of thought prompting, telling the model to show its work. But AIPO 2.0 avoided that. Why?
Because in a system with 50 hard constraints, a longer chain of thought is just a longer chain with more places to break.
Right.
The guardrail approach is just more robust. Instead of asking the model to show its steps, the guardrails restrict which reasoning paths are even possible, which stops it from ever generating a plausible sounding but ultimately wrong answer.
Makes sense.
And for governance, the whole inventory policy is externalized into a plain text file, businessrules.txt. This is brilliant. It means a domain expert can review and suggest policy changes with zero code, without ever looking at the model. It's total transparency.
Okay, so we have this incredibly disciplined process. What does it actually produce in the real world? Let's talk about those audit results. The sources are clear. The audit was focused on decision, quality, rule compliance, explainability, not just raw forecast accuracy.
And the proof is pretty staggering. They tested it across 593 individual SKUs, a huge cross-section of an inventory portfolio. And across that whole sample, the system got a 100% pass-S rate on logic integrity and mathematical precision. That's compliance.
A 100% pass rate on compliance in a domain this complex that's almost unheard of.
It really speaks to the power of that deterministic Python layer, just enforcing the rules. And what's more, they had this validated by two other large models, OpenAI's ChatGPT 5.2 and Grok. When those AIs reviewed the AIPO outputs, they also confirmed it was sticking to the rules.
I love how the governance process showed its real value during that audit. You mentioned some items were initially flagged as fails. What did that look like?
So for example, the system might have suggested ordering a quantity that was a little less than a standard block size, even though policy says order in full blocks. The model was doing this because demand was super uncertain or even zero.
And when a human expert looked at it,
They flipped those fails to passes. Why? Because the system was acting like a senior planner. It was designed to flag uncertainty for human governance. It was effectively saying, hey, I see the rule, but based on the actual demand signal, I recommend ordering conservatively and raising an alert. It didn't make a silent mistake. It forced a human to look where the risk was.
that is the absolute hallmark of a trustworthy system. It resists being blindly confident.
Yes. It proved the system wasn't just blindly copying old orders when the context had changed. And instead of being a black box, it surfaced explicit alert rationales for 84% of the audited portfolio. Every decision was traceable.
For the listener who loves the debugging process, let's pull back the curtain on those systematic failures they found during development. The logic traps. These sound fascinating.
The first big one was the semantic bias, which they called the 4-8 trap. The model was getting confused between the reorder point, which is just a trigger, and the target quantity, the actual amount to order.
Why was it getting confused?
It was the language. The internal variable names. The model's general linguistic training made it latch onto the number 48 and the word order that were near each other in the variable name. It literally got distracted by the word choice.
So the fix wasn't more math, it was better naming.
Exactly. They had to linguistically starve the model of the distraction by renaming the variable to something like safety stock trigger. It just proves that with LLMs, the linguistic side matters just as much as the logic.
Okay, the next trap was the hierarchy collapse. It sounds like a classic case of conflicting rules.
It was. The model had two rules. P1, top priority, was mathematical coverage. P2 was strict adherence to standard block sizes. The model kept prioritizing P2 over P1.
So it was prioritizing neat, round numbers over actually having enough stock on the shelf.
You got it. It saw the block size as a ceiling, not a minimum, which would guarantee stockouts. It just couldn't grasp the relationship between the rules. The fix was to explicitly train the model on the priority hierarchy itself, forcing it to learn that coverage always comes before rounding.
And finally, a failure mode specific to deployment silent stagnation.
Yeah, this is a huge risk with quantization. Normal code, it cries loudly, it fails, and you know it. But LLMs, they degrade gracefully. A botched model update can result in a subtle drift that looks fine until it hits an edge case weeks later. It's a silent failure.
So what's the fix?
They implemented sanity check blocks in that deterministic Python layer. They're just hard-coded logic gates that reject any output if it deviates too far from a simple known baseline. It forces a system override. It just reiterates that core principle. Your probabilistic system always needs a deterministic supervisor.
That architecture, born from failure and hardened by audit, it just makes perfect sense. So to wrap this all up, what's the big conceptual takeaway here for anyone thinking about AI in these kinds of constrained domains?
The main contribution is really redefining fine-tuning. It's not a learning process in the traditional sense. It's an engineering control mechanism. It's a way to constrain the space of possible reasoning paths to make sure the model operates strictly within your non-negotiable business rules.
So the success of a system like AIPO isn't measured by its predictive accuracy, but by its stability under novelty, its compliance with invariant rules, and its absolute auditability. It's about tuning the LLM from a fragile predictor into a reliable, constraint-aware reasoning component. And here's a final thought for you to explore. The research observed something fascinating. When they tried using other AI tools to help generate more of these guardrail fine-tuning examples, the AI helpers consistently fell back into that flawed, outcome-centric approach. They just copied the bad habits they saw in their own training data. This really underscores the finding that conceptual authority in these constrained systems has to remain human-led. Trustworthy AI is built by deliberately constraining it with human insight, not by just delegating control and hoping for the best.